So my talk is about the automated visual inspection with MATLAB. So let's first start defining what we mean by automated inspection. Is everybody doing the inspection in your work? It's an automated process of visually inspecting manufacturing parts for failure and defects. So there are various other terms using for this process if you are using that. Automated defect detection, machine vision, visual inspection, or called optical inspection, or any kind of automated inspection. So that's the industry using different terms on this. But I will start from two examples to showcase how our customer using the visual inspection. So the first example is from ASML. It's a well-known semiconductor instrument manufacturing. They use the virtual metrology technology for semiconductor manufacturing using machine learning. So in the nano fabrication, the photolithography is the fundamental patterning step to control the size of the microchip. So they basically have no idea how to use the machine learning technology, and then they use the MATLAB to create and train a neural network that predict the overlay metrology from alignment metrology. So I just want to clarify, do you know what the metrology mean? Basically, it's the measurement, right? The measurement of the with the very high accuracy. So they basically use the MATLAB to create a neural network to help them to do this. So the second example is from the company called Dexeryl. So basically, it's the Sony chemical. In 10 years ago, they changed their name, formed this new company. What they are doing is the film manufacturing. So they have a phenomenal technology to basically want to find a deep learning technology to process the loss of the data, and then through the transfer learning and deploy via the MATLAB compiler. So that's basically the two examples of how the industry using the MATLAB trying to do this. I just want to give you a few use cases for this visual inspection. So the visual inspection has been used for consumer electronics or the wafer inspection. So they have a few use cases like metrology, like what I mean by measurement. So several other companies, actually a lot of the semiconductor or consumer electronics company using our tool for the metrology design. So second one is called fiducial localization. So basically that's another term is basically reference. So how to find a reference in a pattern. So like the fiducial marker. So basically find a reference. The third one is the quality control, like to do the defect detection. The last one is the anomaly detection. So you can see the soldering like in the PCB board or some of the crack during your production. The data, so data is important right now. What we are talking about mostly is the image data. So either from the camera, the optical images, or microscopy images, or X-ray, CT images. Basically, it's the images. So we are trying to get a workflow that's a very typical visual inspection system. So on the bottom, what you see, there's a wafer has been in production. And then inspection camera take those pictures. What I use, I didn't find a wafer picture, so I use a PCB board with the soldering on site. But basically, that's a picture of those systems. And then through some of the image analysis and find the defects. So that's what we are trying to do. That's the workflow. Those are very complex system and solution, but for this talk, we just want to simplify the process. There's some other, like the manufacturing belt. For example, the Amazon, they have the conveyor, like from the airport, you get your luggage. They have lots of the packages in those belt. So basically, one example is that they want to align the package together so that it's not missed, or they can do some defect detection to see which package is broken or not. So that's a few examples. So you have those manufacturing belt with parts on it, one inspection camera that capture those images, and then the system that analyze those images, classify those are good or defective. That's basically the workflow we want to attack today. So there's two images, one on the left, which I think is good image, or on the right side, there's a few defects. Can you use your eyes to identify those problems or defects? Basically, the machine or camera is trying to do the same thing. Another example is called the defect classification, right? So there are different type of the defects. So probably some of the soldering, the pad is misaligned or connect to others. So there are different kind of the defects. So the second term is called the anomaly detection. So there's some on the PCB board, there's the crack, or they may impact of the signal integrity or some others. So that's the anomaly detection. The third one application is they call the counting or localization or the presence. So for example, you want to find like how many soldering pad in one picture, or where they are, or in some case detecting the presence or absence of those parts, or some parts is missing, or that's what we are trying to do. I'm going forward to show you some of the example how we do those classification and detection techniques using MATLAB. So those are kind of like the old technologies in MATLAB, but we are trying to apply those to these new challenges. So the defect detection workflow, or we call it the defect detection deep learning workflow, consists of 4 main steps. So you may sound familiar, but we just give you a workflow. Number 1, the data pre-processing. So the first stage is that we got a lot of data. We got the image data from the X-ray or camera. Those are terabytes, huge, and stored somewhere, or the production data. We want to clean them up before we do anything for the algorithm. So that's what we call the pre-processing. So this one actually is very powerful using MATLAB. I will show you a few examples. So the second one is that we are trying to use AI modeling and trying to develop some algorithm to simulate and test and to see if our algorithm is accurate or not. It's also important to know that the workflow, after we have the algorithm ready, we need to deploy. So then the algorithm could be in MATLAB, but eventually we want to make that into a like C code or compile to real machine. Then we can get those defects out of the belt, right? So, and often those process is not a linear. You need to kind of like iterate from the beginning and later and see if the algorithm is effective or not. If not, then we may want to go back. So let's talk about those one by one. So start from the data pre-processing. So specifically, we want to discuss the 3 most common questions we want to address. So number 1 is how do I know the pre-process the data to get the right feature? So for example, we want to find some of the features from tons of the boards. And the number 2 is how do I label my data faster? Have you seen like thousands of the image data and you want to label them? Is there anybody has doing those tedious job before? Like just the label, okay, which one is correct, which one is wrong, and then you want to find some features. That can take like weeks, months to even just the labeling. So the third question is what if we have an imbalanced data set? So what I mean by imbalanced means, so some of the data you may label too much, or you just have a small data set you label. What I mean by label is ground truth. So basically you know that's a defects, right? So as the golden reference. Okay, so let's talk about those one by one. So how do I pre-process the data and get the right feature? So one example is that we show you how to segment the image and create a binary mask using an app we call the color threshold app. So what this useful is On the front side, basically it's the soldering, those soldering pad. On the back end is that PCB board, right? So basically you want to detach those to the two layers, and by using this app, you can easily do that by adjust those color threshold, right? So just basically it's the app, but you can easily do your job. You don't need to manually program and then to do this. That's basically how we just play that, and then you see how this app is working. So the second example is that we call the image region analyzer. So that's another app. We basically measure a set of the properties for each connected components. Also, we call the object or region. So this one is the binary region. And you can also use this one to create other binary images. And then the result is you can select and visualize the region by property. You see this, the soldering board has been layered into different color. So the third one, what I want to show you is called the registration estimator. So what I mean by the registration estimator is to offer several registration techniques using feature-based, intensity-based, and non-grid registration algorithm. So there are some specific trials I mentioned here, like phrase correction, MSER, and the surf. So those are just the algorithm. But basically what I want to do is I want to find the several pictures for the same board. And then you want to see those connections. And then using this app, you can easily align different pictures together and to see those features. So what I want to show you, just the three examples of the MATLAB app in this area. But eventually we have a lot of the different image processing and the computer vision app to help you do this job. So you may be familiar about the camera calibrator, color thresholder. You know, the app, I just give you one example. After you do that app thing and try that works, and then you can also export the images or generate some function. So that's the MATLAB code. You can generate it using the app. So, okay, that's number one. So number two is how do I label my data faster? There's tons of the functions on the labeling as well. So one example is that we call the image labeler. By doing this is the dedicated labeling tool. So first you need to do the labeling data. This enables you to label ground truth data in a collection of the images. For like object detection, you can define the rectangle ROI labels like you see here. If you know the MATLAB algorithm can make a mask of defective area, you can also automate the labeling. So what you see here is that you can select the MATLAB class you define, and then you can automate, and then select all of them. That's basically a different labeler. And then from the PCB board, you can see all of those has been labeled. Ground truth label. You don't need to basically manually do that one by one, right? So that's one example. There are other, what I just showed is the image labeler, but we still have the ground truth labeler, signal labeler, which is not image-based. So it can be a signal-based, like audio signal, or that's more like a signal processing to label, video labeler, and blocked image labeler, LiDAR labeler. We have different labeler trying to make this task easier for you to do. So the third question we often ask ourselves is, what if we have imbalanced data set? So this one basically is you start training your deep learning model, but how can we be confident the data you have is enough? You need more data to get to a higher accuracy, or get a model be robust, or use a different model that simply require more data. There's the way we call the data augmentation by transformation. Right? So you have your original data set, and then you can rotate that data set, or you can reflection, so basically the mirror reflection, or you can warping, kind of like twist it, or contrast the jitter on the grayscale, and the hue jitter, basically the different color. Then you can create multiple massive data based on the original one. This one is basically using the deep learning augmentation to create more data for your training. So there's another useful approach to create the data, which is that we use the GANs, called the generative adversarial networks. So these networks basically can create a synthetic image from the noise. What you see is that the video is showing how these GANs are creating new images and the digits from random noise. So this from the random noise, I ask them to create from 0 to 9. That's the results, what you can see. So this basically is using the deep learning to improve your deep learning, right? So that's the first one for the pre-processing. So right now, the MATLAB is very powerful about the pre-processing. So you may be familiar, the image processing and the computer vision, that's even some of the people using the Python or open source to develop the AI algorithm still using the MATLAB for the data pre-processing. So let's get into this specific, what I'm talking about for the deep learning workflow. That's basically in the center of how we use the AI to model and how we simulate and test. So there are 3 types of the defect detection, what I'm just talking about: the classification, anomaly detection, and the counting presence and the localization of the objects. Those are 3 types of the problem. We are going to talk them one by one. So let's start from this example talking about the classification. This data set actually is from Taiwan. So you guys should be proud of that. The professor from National Taiwan University, MIR lab, shared this data set publicly. As the AI getting popular, the data is really crucial, right? So some of our partner company like ASML, Lam Research, KLA Tencor, they won't share the data with us. Or the TSMC or Samsung, Intel, they won't really share the data. So we basically use some of the public data set. That's the WM811K wafer defect map data from National Taiwan University, this lab. They actually contain 811,000 wafer maps images, including 172,000 labeled images. So basically, roughly 20% of the data is labeled. Each of the image has only 3 pixel value. So 0 means that's background, 1 means that's the correct behaving dice, and the value 2 means that there's defects. So there are 9 types of the defects here. So basically, we want to classify which type of the defects this wafer data has. So that's the training data we have. The size of the data is about 3.5 gigabytes. You can download publicly. So here's how that works, right? So that's the one example in MATLAB Deep Learning Toolbox. They show we start from this pre-processed data and augment data. I just talked about this. You load the data and then pre-process it. Then you remove those unlabeled images. It's just one line of the MATLAB code. And then you can see this. That's the explored data set. That's 9 types of the different defects. And then we have the class balancing. So you don't want some of the data is too much, some of the data is too less. So basically you want to balance those. And then you start to partition the data into the different buckets, augment the training data using just talk about how to augment those labeled data. And then we start to create the network, right? So that's before the talk. So let's pause here because I want to talk about for this example, we use the convolutional neural network, the CNN. So I won't go too much about how the CNN works, but I want to mention that so this classical deep learning classification method are not very good for the defect detection use case, where the fault can vary a lot since they are trained on very specific set of classes. For example, the flower, cup, car, tree, right? or cats or dogs. So basically, we want to change a little bit for some of the layer in this network to make it work. What we do is you see they have the edges, shapes, and objects in the different layer. And then the MATLAB basically have an app to help you to do this job. So we call that is the Deep Network Designer. So this app basically can visualize the network architecture. So that's go back to the wafer example. Then we create this CNN network and trying to do this job using the CNN. So here's the approach that we are going to try. We pass the image through the already trained CNN, but we are not really interested in the class in which it is trained, only the first layer to get the feature. Let's stop there and extract those. So you will see this data is getting the pre-trained network, and then we don't need the last few layers, and then we get this one. So this image shows what filter look like and what you can see the searching for. They find in the NUTS image, bright means the good match between the filter and the image. So suppose we already trained that. This task may take hours to finish or even weeks to finish. So we have the GPU. If you have the GPU, you can accelerate this one training speed. So by this example, I just want to show you, okay, if you can have a GPU, you can make your training much faster. It could be like 60 times faster. That's how this one works. So we show one example about the MATLAB code, and then train the network with the CPU. So actually, the setup is pretty simple. It's just define which GPU you're going to use on your premise, and then you can just train and download the network and then start to train that. Okay, so after you train your data, this matrix, so basically we give you we call the performance matrix, called the confusion matrix. So basically you see that for the different type of the 9 predictive classes and then the true classes, how much they can be detected. So you have a confidence that how well the model you just trained. So that's basically the first defect classification. So the second example I'm going to show is the anomaly detection. So we just released a library. This one is the free library download on top of the computer vision toolbox, just released in 24B for the efficient AD. So it's the automated visual inspection library. The library has multiple anomaly detection model like patch core, fast flow, FCDD. So those are already there. Only the efficient AD is the new release on the 24B. You can download and try it out. So I won't go too much details about this efficient AD. So basically, that's a model we already included in the MATLAB. That's a pre-trained model to do the anomaly detection. You can start from this. The easiest way is this patch core model. So the advantage of this patch core, it uses the pre-trained network and doesn't need to retrain. You can also train the patch core model with only normal data. So that's a reliable method that achieves the state-of-the-art results at the time of the publication. So many customers already use the very simple this one to do the anomaly detection, and the results actually are very positive. So one function we just have is that we call the anomaly threshold function. It's one to find the optimal anomaly threshold from the receiver operating characteristic curve. So as you can see on the right side, right? So what is the ROC, like receiver operating characteristic? So this one plot shows the false positive rate on the horizontal axis and the true positive rate on the vertical axis. So the axis is the false positive. The y-axis is the true positive. Ideally, that corner here should be the best. So basically, there's a 0 false positive, and everything is positive is true. So then we can see like every anomaly is detected, and none of them is missed. So that's the ideal. And then we can have this anomaly threshold function to automatically get the best threshold from this ROC curve. So 3 types of the property are supported. Then you don't need to program to see what this threshold should be. There's 3 types of the property you can change. There's some other tools you can evaluate. They call the elevate anomaly detection function and also view anomaly detection results. So those functions just give you some visualization, and then you can play with it. There's 4 detectors. We added different capabilities to meet the different real-time and the memory requirement. That has been used for the different customers. You can start from the patch core. That's the earliest one. And then we just add the efficient AD to the bottom. So now you have a dedicated support package for the automated visual inspection library. And then we want to do this one like for the imbalanced data set. Then we start from this using the full convolutional data description, we call the FCDD, quick to train and require very few anomaly samples. And this one can automatically generate a heat map. Let's go back to the wafer data, right? So using the convolutional data description. So we have a heat map to see like if your detection is correct or not. Then you can have a confidence of that. There's a few challenges, definitely, for these deep learning models when we have. So number one is I don't know if my anomaly detection is accurate or not. The anomaly map is helping to understand that. So what you see here, there are 2 examples on the left side. So we classify the keyboard because of not of the keyboard. That's because of that's next to a mouse. And most likely that will be a keyboard. So by using that model, you can see the heat map actually is not in the keyboard, but on the mouse. Then you see the image data, the feature is more on the mouse, give us a hint, we got the keyboard. So the other example is the crack is highlighted in the anomaly detection. You see those crack over there actually give me the feature. We use those data to basically say there's a crack on your products. Those are basically the MATLAB can give you those heat map after you train a model. Okay, so let's go to my last example for this counting presence and localization. So there are, like, I still use this PCB board because that's the mostly available on the internet, what we can use publicly. We just have this, we call YOLOX. Based on is the anchor-free version of the YOLO. So YOLO is the framework of the deep learning, equipped it with some recent advanced detection techniques like the decoupled head, anchor-free, and advanced label assigning strategy. YOLO-X achieves a better trade-off between the speed and accuracy. So then you can get your model much faster. That's basically using this model, we see those miss soldering pad from this image. What architecture actually you choose eventually? I just talk about they have the traditional like CNN, the more advanced FCDD, or the GN, or there are too much. So I don't know like the answer of the classification and the object detection or the segmentation or the anomaly detection depends on what kind of the training data you have access, right? And the amount of the data imbalance in your data, or what kind of the information you require as an interference time. So they're all going to impact on which model or which architecture you're going to use. But you can start from the basic one and then gradually to tune your algorithm. So the last topic, after you have a model, then we're going to think about the deployment. So the nice thing is after you have those anomaly detection, object detection, we can easily combine with the other toolbox in the MATLAB, like the image library, the CT that image, and the medical image toolbox for the CT data processing. For the deployment, after you have the algorithm, the MATLAB enable you to deploy your deep learning network from a single source in MATLAB onto the different type of the embedded hardware platform, such as the NVIDIA GPU, Intel ARM CPU, or on the cloud. You basically can deploy your C code to the different platform. So this one gives you lots of the flexibility to explore and target different hardware. Basically, we can generate the native optimized code for multiple framework, starting from the low power embedded device, like in the car, like MCU, or the low cost board, like Raspberry Pi, or some other IoT application like sensor and controller in the factory. So that's the other language interface. I know that you may use open source or other C++ library, JavaScript. So they all can be called from MATLAB, then bring into the same environment. Or we provide a flexible two-way integration with other programming. So as you know, the MATLAB and the Python, just for example, can call each other. So you can bring the Python code to MATLAB, or you can call MATLAB function in your Python environment. So right now, it's all supported. We see for example, you already have your algorithm. You can easily deploy it as a desktop or web app. You can also share that app with your colleagues. Easily you can compile and move that to the cloud. Then on the left side, you see that's the Jensen GPU. In the middle, that's the ARM Cortex microprocessor, and also the Xilinx board. So then basically you can deploy it to different platforms. So that's what I'm talking about today. So that's a deep learning workflow that's iterative. So the MATLAB is really shine at the data preparation and also the deployment, as well as the iterative design of your deep learning algorithm, also interop with the Python or the other framework. This one is just a key takeaway I talk about. Interactive. You see those deep learning, the different layers. You can explore and easy to use apps. You don't need to code by yourself. And the flexibility and the options to choose different networks is already pre-trained, is available, it's in the MATLAB, and also give you an easy and extensible framework for the visual inspection from data access to deployment. So that's it. Hope you understand about the workflow and that you can start to use that in your day-to-day job. So hopefully I can see some of the phenomenal visual inspection, saving lots of the costs for your company developed by MATLAB. So thank you very much.